So speaking of midterm, we haven't finished grading it. We're hoping to finish the grading of your midterm by next week. And we'll be using GradeScope for managing everything. Everything is scanned and it's going to be digital. There's going to be a new homework that's due because, we are in the second half of the semester and I can't let you go a week without a homework. So there'll be homework 4 on Thursday. And this one is going to be all about computational learning theory. You'll be proving VC dimensions and such things, things that you did not really get to do before the break. And there'll be no programming, so it's entirely math. I know that some of you were telling me that the programming load in this class is a little too much. So we decided we're going to make it a fully math homework. And then another homework will be no maths, just programming. There's also a project milestone that's due on Thursday. Some of you have been sending messages about this, and I wanted to spend a minute or two discussing that. For this milestone, you are going to have to submit at least one, feel free to do more, at least one non-dummy submission. What I mean by a non-dummy submission is it should not be the all positive or half positive, half negative sample solutions that we gave you. It has to be the output of some classifier that you've trained. Another question that came up was, are you allowed to change it after this thing is done, or is this thing that you submit going to count towards the final set? It's your choice. At the end of the semester, I need 6 submissions that you have marked out as your official submissions. This could be one of them. It doesn't have to be one of them. Maybe after this, you submit this, you find a bug in your code, and you realize that you want to change it. Feel free to change it. That's fine. I need you to have done something towards the submission. It should be the output of some classifier that you've trained. You also need to write a small report on what you did. Don't make it too long. It could be a paragraph. It has to be less than a page for sure. Bullet points are okay. Basically, I need to know what you did and what your plans are for the rest of the semester. The goal of this milestone is to make sure that you are, making progress on the project. In fact, the real goal of this milestone is, if I did not have this, then you will be stressed out at the end of the semester because you have to do a lot of work. Essentially, I'm trying to force you to spread out the work through the semester. So this is not as easy as your first project submission, where you just had to download a file and upload it again. Here, you actually need to train a model on the training data that we have given you. The good news is you can use any of the algorithms that you've already implemented in your homework for doing that. And the even better news is if you felt like in your homework your code had a bug or you had some trouble understanding something, this is your chance to revisit that. You could kind of use the code again. You can fix your code, and the homework code could be the basis of all the things that you do for your projects. Any questions? Yes.
On the topic of unique submissions at the end, we need 6.
Yes.
Total. Is that 6 unique algorithms?
Yes.
Or could we have like variants of one algorithm and have that count for multiple?
Okay, that's a good question. There are some rules about that in the write-up, and I'll tell you what I remember from memory. I want 6 different algorithms, but what I really mean by that is a little bit more than just 6 different algorithms. So let me explain. Perceptron and all its variants will count as one algorithm. Decision trees and all its variant would count as one algorithm. But let's say you have perceptron on the data that we've provided, and then you do some feature transformations on the data and run perceptron again. That counts as 2 different. So a combination of feature and algorithm has to be unique. Okay, so you could do all sorts of feature transformations. In fact, I'll give you a big hint. It turns out that there's a certain feature transformation on this data that we've provided that actually does a fairly better job than the raw data that we've given. I can give you a bit more, but I'll let you explore it and figure it out. We can talk about it again. So to answer your question, a unique algorithm is, what I mean by that is a family of algorithms and a feature set together form a unique algorithm. Question on Zoom. When we submit a CSV file, what does the public score indicate? So your Kaggle predictions that you submit should be on the data that's in this anonymized evaluation file. So we call it, I think, eval.anon something. So there's in this particular file, you'll find that all the labels are 1. Of course, all the labels in those examples are not 1. We've basically forced all the labels to be 1 so that we don't give you the label. So your algorithm has to, your classifier that you train has to make predictions on that data in the format that is described in Kaggle. When you upload those predictions, I don't remember how many evaluation examples are there. If anyone remembers, you can tell me. What we have done is we have split this data, these examples, into 2 parts. 50% of them will, so what Kaggle will do is it will take all your predictions and partition them into 2 groups. Half of them will be, and each of those will be evaluated against the ground truth label that Kaggle has. One half of them is called the public evaluation, the other half is the private. You will only be shown the accuracy score or the F score on the public portion of the evaluation examples. The private evaluation, you don't get access to. And there's a reason we are doing that. Imagine that you get access to the entire evaluation score on all of the examples that we've given you. So I don't remember the exact number, so let's make up some numbers here. Let's say there are 1,000 evaluation points, and we give you the accuracy or the F score on all 1,000 examples. Let's say you get an accuracy of 56% or F score of 56%. You could do something very sneaky on that. You could use that number 56 as a reward for training your model so that you start overfitting the test set. You don't get the true label, but there are certain families of learning algorithms that allow you to train using that one reward. And this is a reinforcement learning problem, it turns out. We don't want you to do that. So what we do is we don't give you all the evaluation on all the 1,000 examples. Half of them we evaluate and we show you the performance. The other half is the hidden set. And if you do the sneaky thing and you overfit on those half, then your private evaluation scores will drop. And we know that you've done the sneaky thing. I know that you're not going to do that because it's too much work. But I don't want you to take it as a challenge and do that. Or not. I mean, if you do that, I would be impressed but annoyed. But people have done that in the past. In more high-profile situations, there was a certain public competition where people were asked to compare the classifiers that they trained on a certain data set on a public leaderboard. And it turned out that a certain organization created hundreds and hundreds of accounts and kept submitting responses every few hours to the leaderboard and used the response from the leaderboard to tune the model. And that way they went to the top of the leaderboard. Basically, they overfit on the test set without actually seeing the test labels. That's an interesting learning problem. It's a lot of work. And it turned out that there was a lot of money involved for the people in that organization because their bonuses were tied to their position on the leaderboard. And then it came out and some people got fired. You can't get fired, but don't do that. And it's also a lot of work. You need a lot more resources than you have. But I hope that answers your question. The public score indicates your F score on half of the evaluation examples. Any other questions about projects? Yes.
So we've learned 2 unique algorithms so far.
Yes.
Towards the end of course, are you going to learn 4 more?
You're going to learn a lot more. From now till the end of the semester, you're going to just get so many algorithms that you'll have more than you need. And remember also, one of those 6 things can be an external library. You can use an algorithm that we have not covered in class that's implemented in some library, if you care. We will have enough algorithms that I can just list out. So we've covered decision trees. We've covered perceptron. Today we'll do ensembling. Ensembling is not an algorithm, but ensembling is a strategy for combining multiple predictors to create a consensus. So you could have an ensemble of trees. You could have an ensemble of perceptrons. That's already 4 things. But you could have a feature transformation and then train a perceptron and a decision tree, then you get 6 things already, with using only the things that we have. After that, we will look at support vector machines. We'll look at logistic regression. And we'll look at neural networks in general, which means that if you feel like it, you can even implement a neural network. If time permits, we will cover nearest neighbors. So you'll have enough. I say that, but more often than not, I've been missing nearest neighbors for the last few years because time doesn't ever seem to permit. But I'm hoping we will. That means we'll have enough algorithms between SVM, perceptron, logistic regression, decision trees, and ensembles of all of these things, and the feature transformations. You'll have more than 6. Yes.
So I still have a confusion with like what we're submitting. So like, are we submitting like prediction as?
Yes. So there are 3 files, 3 data files. There's a training set, there's a test set, and the evaluation set. You're going to report the results of the test set in your reports. You're going to submit the predictions on the eval to Kaggle. The reason for that is the train and the test behave like standard train tests. You conduct your experiments locally. Eval is what you need to, it's really 2 kinds of evaluation. One is the local evaluation that you do your tests on. The other one is the public evaluation that's on Kaggle. So for that, you need to do submit the results of predictions on the eval files. Other questions?
Will this course cover like frameworks like PyTorch?
Oh, good question. So this course will not cover frameworks like PyTorch, simply because I do not want you to be tied to one particular learning framework. However, I'm going to ask my TAs, I kind of mentioned it to them at some point. Usually my TAs offer a tutorial on PyTorch each year because they have been working with PyTorch at a very low level, and we give like a high level overview of PyTorch. I don't require that you should attend that tutorial, but if you want, you can. And it ends up being a hands-on tutorial. You can come with your laptop and just work through the process with them. I'll announce that as we go along. It also depends on the TA's availability and such things. If not, I could also ask a senior graduate student to do that. But usually we've been doing that, but not necessarily in the lecture period, but maybe also in the lecture period if time permits. Yes.
I guess, does the order we submit our labels matter, like the example ID order?
Honestly, I don't know. You can try.
Well, I guess if I don't know, like if I submit it, I won't know if it works or not, right? Because I won't see the results.
You do, right? You do see the score on the public data.
Well, so I guess we see half of it, right?
Yeah, that's fine.
Okay.
You should not expect a huge difference between the results that you get on your test set and the evaluation, because they are 2 random samples of the same data. They're 2 random samples from the same distribution, so you should get similar results. That's the first point. The second point is, I suspect, and don't hold me up to this, but I suspect the order of the rows does not matter, because if you remember, the submission file has 2 columns, the example ID and the label. And why provide the example ID if the order matters? I'm hoping it does not. I'm hoping Kaggle does something reasonable, but if it does not, let me know.
Okay.
All right. If there are no other questions, let's talk about boosting and ensembles. But before that, just to kind of keep track of where we are and how we got here, for the entirety of the semester, we've been talking about supervised learning, where instances are assigned labels by concepts, and our goal is to discover a hypothesis that mimics that concept. And to do that, we have a set of examples that we are calling the training set that gets poured into this learning algorithm, and the learning algorithm produces a hypothesis. The hypothesis is a function that can take new examples and make predictions on them. We've looked at 2 specific learning algorithms, decision trees and perceptron, and a bunch of their variants. But along the way, we also looked at high-level machine learning ideas. We've looked at the idea that feature examples, instances, are represented as feature vectors. We've talked about in a fair amount of detail about the concept of overfitting, and we looked at two different ways of addressing the question, can my problem be, is the task learnable? One way of formalizing that question is the mistake bound model, which says a task is learnable if after a certain polynomial number of examples, the learner stops making mistakes. We also looked at another way to answer the same question, which is PAC. And in PAC learning, the idea is that with high probability, your learner has low generalization error. Along the way, we looked at generalization bounds, this concept of sample complexity. We looked at consistent learning and agnostic learning, and we looked at VC dimension. In all cases, the idea was if you have a certain number of examples, and that number of examples, or if you have a certain hypothesis class, and if you have a certain number of examples that crosses a threshold based on the complexity of the hypothesis class, then with high probability, you can guarantee success for learning. Notice that this is a one-sided bound. If you have a certain number of examples with high probability, learning can succeed. What happens if you do not have that number of examples? None of the theory says that learning will fail. It only says if you have those many examples, learning will succeed. If you don't have those many examples, we don't know. Maybe learning will succeed, maybe not. We can't tell. But that's the style of the bounds that we've seen. Any questions about any of this stuff? Let's then dive into ensembles. Rather than presenting ensembles first and then specific algorithms, I would like to tie it to something that we've already covered, namely the PAC learning, and introduce a particular style of ensembling called boosting that essentially stemmed out of PAC learning, and then generalize that to more to broader ensemble methods, which are actually pretty easy to implement. It's a useful tool to have in your toolbox. It's one of those things where if you're willing to pay the computational price, you're going to get 1 or 2% bump in accuracy without actually doing any thinking, which is a nice thing to have. So it's a useful thing to have in your toolbox. So to get started, let's look at what's boosting. Boosting is an answer to a certain question that was posed in the PAC learning context. In this paper called this was the answer. But boosting is more generally an approach for constructing a strong learning algorithm if you have a collection of weak learning algorithms. I'll explain that in a bit. Basically, it's a mechanism for creating a learning algorithm by amplifying the learning capability of rules of thumb that are slightly better than chance. Imagine that you have a collection of rules of thumb about a task that are slightly better than chance. And the question is, can you somehow combine all of them to create a learner that is arbitrarily good, that has PAC guarantees? And it's an instance of an ensemble. An ensemble is nothing but a group of classifiers that have to work together to make a prediction. It could be classifiers, it could be regressors. So the idea is that you have, if you have a task. So far in the semester, we've been looking at, we have some learning task and we train one model to make a prediction. Who says you need to train only one model? Imagine that you are somehow training thousands of different models. They could be different models because you have resampled the data somehow. So each model is slightly different and it may not always agree with each other. And then when a new example comes in, rather than asking any one of those models, you ask all of them for the prediction and you take the majority label. Or maybe if it's a regression problem, you take the average label, average value. Such a system is called an ensemble. An ensemble is nothing but a committee of predictors that are aggregated together to produce a consensus decision. Boosting is an instance of an ensemble. To give an example, to illustrate the problem of boosting, I'm going to use an example that's a slightly modified version of the example that was in Rob Shapir's original paper that introduced us. Imagine that you call a customer service line and your phone call has to get routed to the right person automatically. We've all been there. And let's say that your job is to implement that automatic routing system that listens to your request and sends it to the right place. So if you say, I would like to imagine this is a bank, and you say, I'd like to know my account balance, then it goes to a service that is dedicated to account balances. So for this particular input, the label is balances. If you want to know when the bank opens on Monday, it goes to a dedicated system that answers questions about the hours of the bank. If you're unable to log into the app, then it goes to a desk that's supposed to a help desk for online services. Maybe you can come up with easy sort of heuristics, rules of thumb that can solve this. So maybe if the word login is mentioned in the request, you automatically send it to online services. Because nobody's going to say, I would like to log into your bank on Monday, what time is it available? I don't know, maybe they do, but more often than not, when they say login, maybe it's about account balance. Not always right. Sorry, it's about online services. Not always right, but it might be slightly better than chance. But that doesn't mean that every instance of online services is going to have the word login. Right? Maybe instead of saying I'm unable to log into my account, you can say, can I? The app is missing in the App Store. And turns out the word login doesn't show up there. You don't know where to route it. So maybe if the word app shows up, you send it to online services. You can write these kinds of rules of thumb, right? You just look for common words, and if the word shows up, you send it to the right place. Can you imagine doing that? Can you come up with those kinds of rules? Could you invent them? Can someone tell me what would be a sort of a silly rule that will take you to hours? Yeah?
If the word hours is in the phrase?
If the word hours is in the phrase, in the request, you route it to hours. This is a whole bunch of if then else rules. Right? There's no machine learning here. There is not yet. And let's pretend that every one of those rules is slightly better than chance. So then the question is, can you come up with a consensus program that somehow combines these rules to produce a model that is as good as any learned model that you can train on data, if you have data for this? So can you train a classifier that combines all these rules and then somehow produces a classifier that's better than any one of these rules? Because these rules are only slightly better than chance. That's the problem that we are trying to solve here. And here's a boosting approach. And this is an idea that you might think of when you're inventing these rules. Maybe you have 1,000 examples. You pick 3 examples, all of which have the label online services. You look for what's common in that. Maybe the word app shows up. So you invent a new rule. And you say, if the word app shows up, it's online service. Then you pick 3 other random examples. And then you see that the word hours shows up. And every time it shows up, it's in the context of, so whatever that label was, hours. And you invent a new rule. So you can keep doing this. You pick a small subset of examples, you invent a new rule, and you add it to your list of rules. Now, at test time, when a new example comes in, you apply all the rules, and if only one of them fires, you route it there. If multiple of them fire, you need to figure out how important each one is. If you had a mechanism for somehow combining those rules, then you route it to the right place. This process so there are 2 steps here. How do you discover new rules? And the second one is, how do you combine them so that you can come up with a consensus? Okay, this is the high level question. So we need to discover new rules. Well, let's think about it. How do you discover new rules? Do we have any algorithm that can take data and find a rule from it? Yes.
The ID3 algorithm?
The ID3 could do that. And if you want to be less sort of picky about it, you could also say the perceptron could do it. Right? You give it some data because these examples are labeled, right? You could give it to perceptron and just find a classifier. Any learning algorithm can do the job. So the problem of deriving a rule is nothing but a learning problem. But can you be clever about selecting those subsets? If you pick those subsets just the right way, maybe you're able to discover a good rule. And maybe you can do that efficiently. So that's one question. How do we select these subsets? Another question is, how do you combine all those rules? Maybe the two rules could apply on the same instance and they disagree with each other. So whom do you trust? That's the other question. So if you can answer both these questions, then you have invented a boosting algorithm. Yes.
We select the subsets by finding subsets with minimal entropy.
You could. That's an algorithm that you've invented. Minimal entropy, another way of thinking about that is, what if all of the examples have the same label? That's as low an entropy as you can get. But is that good enough? Because maybe you have a very diverse set of inputs that you're having a hard time discovering a rule. Your learning algorithm, that rule discovery algorithm, for this lecture, let's assume it's a very weak learner. It's not great at discovering complex patterns from data for now. But you're inventing new strategies. Boosting is a general method for converting these sorts of rough rules of thumb into accurate classifiers. Any questions so far? Yes.
Does the number of rules of thumb matter in this case?
Very much yes. Eventually, I'll show you a theorem where that becomes a complexity parameter. This is for boosting. Boosting comes with stronger theoretical guarantees than other ensembles. And that theoretical guarantee depends on the number of rules of thumb. Yes.
Is it like with the more rules we have, or more like sub-classifiers? Are we like guaranteed a higher accuracy?
On the training set. On the training set. I mean, that's literally the theorem. As the number of rules increases, the training accuracy drops exponentially for boosting. There is no such guarantee for generalization, but we've seen results that for pack guarantee, generalization performance is not too far off from the training set, provided certain conditions hold. So those things kick in for boosting. For other ensembles and ensembles in general, there's no guarantee that your performance is going to get better. But I have to say, every time I have seen an ensemble, you get a 2% bump. So it almost seems like there is some sweet spot there where there are a few different caveats. The first one is you have to train each of these rules of thumb, which itself could take a lot of compute. So you don't want to train 1 million rules of thumb because A, you have to train them, and B, at deployment, you're going to actually predict all of them. So it's going to be slow. So if you're ensembling, there is a certain sweet spot in terms of how many sub-classifiers you have, because it increases the amount of compute that you need to use at deployment. So there's also those practical factors come in. Okay, let's formalize this a little bit. We've seen pack learning. I'm going to, everything that I defined as a pack guarantee, for today's lecture, I'm going to call it a strong pack guarantee. A pack algorithm is one where no matter what distribution you have over the examples, for every single error threshold and every single delta, that's the guarantee for learning, which is just all you need is for the both of those to be positive. A strong pack algorithm will find a classifier whose error is less than epsilon with high probability using only a polynomial number of examples that are randomly taken from this distribution. We've seen this. Basically, no matter which epsilon we have, no matter what delta we have, using a polynomial number of algorithms, polynomial number of examples, this algorithm will find a classifier whose error is less than epsilon, and it will do so with probability 1 minus delta. Let's look at this epsilon here. For every epsilon greater than 0, no matter what your desired epsilon is, if I want a very low error, if your error threshold is somewhere here, there's a certain number of examples, which is polynomial in 1 over epsilon, that you need. If you are okay with a really bad classifier that's just slightly better than chance, the error is less than half, then you probably need fewer examples, but even for that epsilon, this algorithm will work. Depending on how good or bad a classifier you want, this algorithm will work. That's what a pack guarantee gives you. Now, let's say that we don't have such an algorithm. Instead, what we have is what I'm calling a weak pack algorithm. It's doing all the same thing, but this epsilon is half minus gamma for some small gamma. So that means, imagine that this is gamma, that gap there. Epsilon is slightly less than chance. So it's between, your error lies in this region here. It's just, if it is 50%, if you are assuming that your pluses and minuses are equally distributed, if your error is more than 50%, that's not even a good learner. If your error is more than 50%, then all you have to do is you ask your classifier for a label and you just return the opposite label, you'll do better than chance. So let's not worry about this side at all. This does not exist in our world. Imagine that your learning algorithm can give you a classifier for some that has an error that's just slightly better than chance, which means the error is slightly better than 50%. It can do that no matter what. So for every distribution over the examples, for every delta greater than 0, given only a polynomial number of examples, your weak learner will give you a classifier whose error is slightly better than chance, better than random guessing. This is what boosting calls a rule of thumb. A rule of thumb is something that does better than chance, but is really not great. Ideally, you want epsilon to be small. Ideally, you would like to live in this region here. You want your epsilon to be small, but your rule of thumb does not really apply most of the time. So for the most part, it's as good as random guessing. For the places where the rule of thumb applies, it's going to do better than chance. So on an average, it's slightly better than chance. So for instance, if your gamma is 0.01, your error is going to be more than 0.49, but less than half. Yes.
So our rules of thumb are weak pack algorithms. then.
The system that generates the rules of thumb are the weak pack algorithms. So the pack algorithm is a learner. The learning algorithm that produces a rule of thumb is the weak pack algorithm. So it's a weak learner, it produces a weak classifier. Okay? So we have two kinds of pack algorithms. This thing that we called pack before, I'm calling it strong. It's true. It's going to produce, for no matter how much epsilon you have, how low an epsilon you have, it will produce a classifier. I'll come to the question on Zoom in a minute. The weak pack algorithm will give you, no matter what distribution of examples, it will give you a classifier that's slightly better than chance. The question on Zoom is, I said a few times that boosting can give you 1 to 2% improvement, but how could we stack that on top of a previous algorithm? How do we prioritize other algorithm results and whatever boosting does? It turns out boosting internally uses other algorithms. The weak learner is the thing that's sitting inside boosting or any ensemble, and the ensemble is going to build on top of that by calling your weak learner again and again as a subroutine. Hopefully the answer to this becomes a little clearer when we see the actual boosting algorithm. The question that motivates a lot of this is, does weak learnability imply strong learnability? This was a theoretical question in a paper by Michael Kearns and Leslie Valiant from 1988. Suppose you have a certain concept, a concept class, for which you prove the existence of a weak learner. Does this mean there exists some algorithm? Maybe you don't have that algorithm at hand. Does there exist some algorithm for that same concept class that is a strong learner? If a certain concept class is learnable with a weak guarantee, does this mean it's also learnable with a strong guarantee? Can you somehow boost this weak learner by doing something so that you can create a strong path algorithm? It was a theoretical question. It did not talk about any specific algorithm. It just said, if a certain concept class has the property that you can easily derive these rules of thumb that are better than chance, does this mean that concept class is path learnable? Just a theoretical question. And the cool thing was this theoretical question immediately led to a little bit of a cottage industry that tried to answer that question. Very quickly, the question was posed in 1988. In 1989, Rob Shapiro proved that the answer to that question is a yes. Weak learnability implies strong learnability by actually providing an algorithm that internally calls the weak learner 3 times on 3 modified distributions over the data. Basically, rather than messing with the examples, it modifies the underlying distribution of the examples. And calling the weak learner 3 times, he showed that by combining those 3 classifiers that you get, your combined classifier will have an error that's better than any of those 3 things. So you get a slight boost. And you recursively keep doing that again and again, you can boost it to arbitrary improvement. That was a neat trick. Independently, Joachim Freund in 1990 showed that there's a certain optimal algorithm that can boost by the majority label. A few others showed practical, some experiments with boosting in 92, but really the compute was not great. And these algorithms, even though they were nice to look at and nice to write papers, they were really not practical algorithms. And in 95, Freund and Shapiro combined forces and they put together their collective understanding of the problem into an algorithm called AdaBoost. AdaBoost came with strong practical advantages because it's actually fairly easy to implement. I'm not going to make you implement in the homework, but it's actually fairly easy to implement. And it also comes with neat theoretical guarantees. A whole bunch of papers and practical applications involving AdaBoost followed this 95 paper, and they got this rather prestigious award called the Gödel Prize for this work. So there's a lesson here about, how science progresses. I'm not sure what it is, but somewhere at the end of that lesson is a Gödel Prize. Okay, history aside, let's look at AdaBoost, the algorithm. First, I'm going to present an intuition for what it is. Then I'll show you the algorithm, and then I'll show you a result that talks about why it works. Here's a toy example. Let's say we have this 2-dimensional data set with pluses and minuses. And of course, as we've done so far, our goal is to build a separator that separates the pluses and the minuses. Of course, it's not linearly separable. But let's even not worry about linear separability. Let's say that your weak learner has only 2 kinds of functions it can pick. It can draw a horizontal line anywhere, or it can draw a vertical line anywhere. Those are the only 2 things it can do. Basically, it tries to find a horizontal line or a vertical line, and that's all your weak learner is capable of. Okay? So let's say that let's now play this game of AdaBoost. An important thing to mention here is AdaBoost associates with every single example a measure of importance assigned to that example in this particular round. How important is each example for the weak learner? And I'll show you examples of that as we go along. Initially, all examples are equally important. We don't know anything about any example, so we have no preference over this. So all the examples have equal importance, and maybe your weak learner picks this hypothesis. Maybe it decides to pick that vertical line that says everything on this side is a plus, everything on the other side is a minus. Let's say this is the best classifier on this data. Okay. So your weak learner has now produced a classifier. So what's the error of this classifier? %30. That's not a trick question. It's basically asking you to divide 3 by 10. So there are 3 examples that are on the wrong side of this separator. And the rest of them are all correct. So the error is clearly 30%. Keep just put a pin on that, because very soon I'll ask you the same question again, but at that time it will be a trick question. I'm telling you right now. What AdaBoost then does is, by the way, first thing to note, internally, AdaBoost has called the weak learner, right? Also, this is not a regular weak learner. This is a weak learner that somehow takes into account the importance of all these examples. Initially, all the examples were equally important, so it didn't really matter. But now there are 3 examples that were incorrect and 7 of them were correct. So AdaBoost will now change the importance of these examples. It will increase the importance of the 3 examples that were mistaken, where there was a mistake, and everything else becomes less important. The size of the font there, think of it as the importance. So 3 examples become more important in the next round. 7 of them become less important. What does it mean to say that they are important or less important? What that means is the next time when you call the weak learner is going to try its best to get the more important examples right. And if it makes a mistake on the less important examples, that's okay. Okay? So that's really what the weak learner has to do. And then now we call AdaBoost again. At each step, now we have this importance, and I'm going to introduce some notation. I'm calling that D sub T. In this case, we have D2. We are currently in round 2. D2 is really a vector, with one element for each example. Maybe this example has a higher importance. So there were originally 10 examples, right? There are 10 examples. Each of them had an importance of 0.1 because each of them is equally important. Maybe this one's gotten a little bit more important, so maybe it is 0.12. This one is 0.12. And this one is, maybe it's become less important, and so on. So every example gets a certain number associated with it, which says how much should the weak learner focus on that example. Any questions about this? Yes.
Does the next week learner have to get the more important ones right, or just like get like an average number?
On an average, it has to. There's a certain formal sense in which it has to do something, but intuitively it has to try to get on an average the important ones right. Eventually, it'll actually fail on that, but at least it has to try. Yes.
The scale of like weight vector.
It's not a weight vector. It's not a weight vector. This is an important confusion that a lot of people have when they see this first. This has nothing to do with weight vector or such things. This is just a number that's associated with each example. Weight vectors are numbers associated with each feature. Here, every single example, there are only 2 dimensions here, right? This is not a weight vector. In fact, weight vectors only apply to algorithms like perceptron. Imagine you have a decision tree. In fact, here we don't have any of those. We just have vertical and horizontal lines. This is a weight associated with examples, which says how important is that example. Formally, actually, what's happening is it's actually, remember we talk about this fixed but unknown distribution over examples? It's reshaping the distribution so that these error examples become more probable. That's what it's actually doing internally. That's what's happening in the math, but practically it's not, that doesn't matter. Okay, so now we have these three examples where the learner has to try to get right, and maybe it finds this particular hypothesis. Once again, a vertical line, but it puts those three examples on the positive side. Okay, it could do that, right? So now the question for you is, what's the error on this of this new hypothesis? 30%.
Yes.
Less than 30%. So who says 30% and who says less than 30% other than the two of you? By the way, when I said there's going to be a trick question, this was it. Yes. And can one of you two justify? Maybe you should, because you.
Because we assign weights to those three positive examples, they have higher value, so those three negatives have less value than average. That is what I was saying.
So there are three mistakes here, right? So the answer that was proposed is, we have these three mistakes, but look, they have less importance. If they have less importance, that means they, even though technically the number of errors is 3 out of 10, the importance of those examples is low enough. Imagine that instead of small, let's pretend that this example had a weight of 0. That will never happen, but let's just pretend that that has a weight of 0. Then it doesn't matter if you make a mistake on that, because that example has a 0 weight. It's almost like, what's the probability of seeing that example? It's 0, so it doesn't matter that example has a mistake. So while in one sense, the error of this classifier can be seen as 30%, for the purposes of boosting, for the purposes of AdaBoost, we are going to use this notion of a weighted error. This should be H2. The classifier H2 that was learned on this data has an error less than 30% because those three examples have weights that are less than 0.1 each. There are 10 examples. If they are all equal weights, then it will be 0.1 each. But because we have demoted them, they have weights less than 0.1, so the total weight has to be less than 0.3. So the total error is less than 0.3. While computing the error, we are going to assign a weight for each example by its corresponding dt. That dt of I for ith example will contribute to the error. So really, the error is the sum over dt of I over for every mistake, for every point where there's a mistake, there are 3 of them here, you add up their weights. That's the definition of error for AdaBoost. It naturally generalizes the standard definition of error. The standard definition of error essentially is saying all the DTs are equal. If every example is equally important, the error is nothing but the fraction of examples where you make a mistake. But if some examples are more important than others, then the error is the total weight of the mistakes. Yes.
So we're basically saying, even though we're getting 3 mistakes wrong, or even though we're getting 3 mistakes on these examples, because these examples are, shall we say, less important, it doesn't matter as much that we are
Yes.
getting.
That's right. That's exactly right. And it's in this context where I said the weak learner has to do better than chance. What I mean by that is this notion of error has to be less than 0.5. That's the hope that we have eventually. There's a formal definition of this error. I'm not going to go over this expression. I will leave it as an exercise for you to think about why this is a reasonable definition. It turns out this is the correct definition of error. It's half minus half times sum over. And the hint here is this blue thing is either 0 or 1, depending on whether this example has a mistake or not. I'll leave it as an exercise for you. And if you're not sure what's going on, I have some slides on how to work through this process. But really, eventually, the error is this quantity here. The error is simply the sum of the weights of over the examples where y and h are not the same. Okay, so now we're done with round 2. We do the same thing again. We have 3 examples where there are mistakes, those 3 circled examples. We increase the weights of those things, and every time there was no mistake, we decrease its importance. So this one gets a little bigger. This one becomes even smaller because you got it right twice. This one has gotten a little bit smaller, but it's still big because you got it wrong once and right once. And these things which you've been getting right twice are now getting even smaller. So we recompute the weights associated with each example. And we're done with round 2. So in each round, we train a new weak classifier using the current weightage for these examples, and then reweight the examples. That's all we do. So now we have this new data set. We are in round 3. We still have this new d sub t, which is the weights associated with each example in this current round. And we need to find a new classifier. Does anyone want to guess what shape that classifier will take? A horizontal line or a vertical line, given these weights? Horizontal? And where would that be? So something like that?
Separating the bigger positives and the bigger negatives. So yeah.
Like that. You're all good weak learners. So the learning algorithm found this horizontal line, and this one also makes 3 mistakes. Actually, it makes more mistakes. It makes 4 mistakes. And yet its error is pretty low. Why? Someone who's not answered before. Someone who's not answered before. Yeah. Well, you've also answered before. Or someone who's not spoken up before today. And if you don't have an answer, ask me a question. There's someone on Zoom who's also answered before, so I'm not going to read out your answer.
The way something correctly labeled examples are correctly labeled, whereas the smaller ones.
That's right. Look at those 4 examples where there are mistakes. All of them are tiny. They are extremely unimportant examples for this round. So when you add up the weights for those examples, it's okay if you make mistakes on them. These examples all have really small weights. And because they have small weights, the error is only 0.14. Even though the actual number of errors is more, it seems like this weak classifier is even better than the previous one. So while computing error, we will weight each example by its d sub t. So we've now completed the next round of AdaBoost. Actually, no, we've not. At this point, to complete this round, we have to reweight these examples. We have to make these 4 examples bigger and everything else smaller. You can keep doing this, right? You can keep doing this forever. We don't have forever, so let's stop. Yes.
Is it the bottom right label correctly labeled?
You're right. That's right. You're absolutely right. So in fact, this one has been labeled, you're absolutely right. So it was not 4 mistakes, it's 3 mistakes. This example has been labeled correctly 3 times in a row. So it's going to get really, really tiny the next time. Yes. Good point. And the answer on Zoom was also the right answer. So those 3 examples will get up weighted. Every other example will get down weighted in the next round. But let's not keep going on. Let's say that we are done. Let's say we are done with the learning process. And so we have these 3 weak classifiers that we've learned, H1, H2, and H3. At prediction time, when a new example comes in, what we do is we ask all 3 of them for a label. And maybe let's say that the new example is somewhere here. We ask all 3 of them for a label, and H1 says minus, H2 says plus, H3 says minus. But we don't just take the most common label. Instead, we assign a certain weight, alpha, and this is not minus and plus, it's -1 and +1. So it's minus alpha 1 plus alpha 2 minus alpha 3, and you take the sign of that. You essentially treat the predictions of these weak learners as features for a bigger classifier whose weights are alpha 1, alpha 2, alpha 3. And you take a linear combination of these predictions and check if it's greater than 0 or less than 0. If it's greater than 0, then you say plus. If it's less than 0, then you say minus. I've not told you where these alphas come from. AdaBoost has a recipe for that. Questions? Yes?
How do we determine at what point we stop generating these sub-hypotheses, these HIs?
There are a few heuristics. One answer is if your HI starts getting worse, meaning it starts doing worse than chance. If its error is more than 50%, the weighted error, then you're essentially, there's no signal that you're pouring into this thing, might as well stop. Another one is it's a hyperparameter. It's like the number of epochs. You just stop after 10 rounds or 100 rounds. You decide upfront. Or another way of thinking about it is you keep doing this and you stop when the error of this combined hypothesis on a held out set starts getting worse. So you do the standard sort of things that you do for picking them as you would do for number of epochs. Cross-validation is another idea. You can think of these alphas as another way to think about this is each of these H1, H2, H3 is going to produce a prediction, a label, a -1 or a +1. The alpha is the number of votes that each classifier gets in this process. If the number of votes H1 gets is more than the number of votes of H2, then for that point that we considered here, maybe that means that alpha 1 would be bigger than alpha 2. Maybe then the label becomes minus because H1 is more important. H1 has a higher number of votes. That's another way to interpret these alphas. In fact, that's another way to also interpret the weights we learned for with the weight vector for perceptron. Any questions about this process, what you've seen so far? Yes.
How do we get the algorithms?
I'll tell you in a minute. So the algorithm basically gives you a recipe for constructing the alpha. Now, one of the cool things about AdaBoost, the algorithm, as opposed to all the other ensembling algorithms out there, is every part of it is very cleanly specified. How do you get the alphas? How do you do the upvoting and the downvoting? And they have very specific recommendations for that. And those are not recommendations. If you choose those approaches as the algorithm specifies, then the theorem works. The theorem associated with this algorithm is designed, or all of these choices are designed so that you are able to prove the theorem. So we'll talk about that in a minute. But at a high level, an outline for this algorithm might look something like this. You have a data set, a fixed data set with m examples. Each example is now working, has a label of -1 or +1. You decide upfront that you're going to continue this game for capital T rounds. In each round, you first construct a distribution over these examples. In the first iteration, the distribution is just a uniform distribution. All examples are equally important. So that's your DT. So this is going to be a list of M numbers. And then the next step is you find a weak hypothesis, a rule of thumb, H sub T, that has a small weighted error, epsilon T. That goes back to the question that you asked. How do you know what is a good weak classifier? I mean, it has a small weighted error. All we need for this theorem to work is that epsilon T should be less than half. That's all we need. In a perfect world, a low epsilon T is good. What I have not told you is how do you modify your existing algorithms so that this property holds, so that it finds a low epsilon T. Keep that question in mind. Imagine that you have to take your decision tree learner or your perceptron and change it so that it gives you a low weighted error. We never really cared about weighted errors so far. Keep that question in mind and think about it. We'll come back to that if time permits. If not, we can. I want you to think about it and come back on Thursday. But even without that, there are two things that are underspecified. How do you construct that distribution, and how do you get those alphas? How do you construct that H final? If I can tell you both those things, then in theory, you have the entire algorithm. This part here, it turns out that most of our standard learning algorithms can be easily tweaked so that they start optimizing for low weighted error. Let's first focus on the first question. How do you construct the D sub T? D sub T is just a set of weights, one number associated with each example. For the theory to work, it's not just a number, but it's actually a distribution. That means these things add up to 1. So it's a distribution, or that's why it's a D, D for distribution. You need to construct a distribution over the examples so that important examples have higher values and unimportant examples have lower values. In the first round, all examples are equally important. You have M examples. D1 of I is 1 over M for all I. Every example has a weight of 1 over M. When you add up 1 over M times, you get a 1. So it's a distribution. So we are good. Now comes the cool bit. Let's say we've run this game for T rounds. What we have is D sub T. And using that D sub T and the data set that we have a hypothesis that your weak learner produced. You were able to evaluate that hypothesis on your data and get the weighted error. And you also have epsilon T. Given HT, you can and DT, you can calculate epsilon T. That's the error. That's what we had before. Using all of these three things, now we need to specify, we need to construct dt plus 1. What do we want from dt plus 1? There are two kinds of examples. There are examples where there's an error. There are examples where there is no error. What we would like is on examples where there's an error, dt plus 1 must take dt and somehow decrease it. Let's call it dt of I, okay? So that we're talking about the ith example here. You should take dt of I and decrease it. On an example where there is sorry, I made a mistake. The other way around. If there's an error, you need to increase it for the next round. This example was a mistake. It becomes more important the next time around. If there's no error, then there was no mistake here. It needs to get demoted. We need to set up a construct mechanism to define this dd plus 1 that has this property. We would like to find, at the next round, we want to find a hypothesis such that has the following property. Examples that were incorrectly predicted in this round become more important the next time around. Examples that were correctly predicted in this round become less important the next time around. To do that, what AdaBoost specifies is dt plus 1 of I is the same as dt of I, but multiplied by a certain quantity. Let's ignore the z for now, because z is there just to make sure that everything adds up to 1. If an example I has no error, that means yi is the same as ht of xi. If there is no error, then you multiply it by e power minus alpha t for a certain alpha. If there is an error, then you multiply with e power plus alpha t. Now let's think about this a little bit carefully. Now suppose alpha t is a number that is, let's say, positive. If alpha is positive, then e power alpha is what?
Positive.
E power alpha is anyway positive, but is it more than 1 or less than 1? If alpha is positive, e power alpha t is more than 1. If alpha is positive, what about e power minus alpha t? It's less than 1. So on an example where there is no mistake, you're multiplying with a number that's less than 1. On an example where there is a mistake, you're multiplying with a number that is more than 1. You multiply with a number more than 1, you're making it bigger. On examples where there are mistakes, d gets bigger. On examples where there are no mistakes, dt gets smaller. dt plus 1 gets smaller. Examples that are correctly labeled are demoted. Examples that are incorrectly labeled are promoted. And the reason for that is we are going to define alpha in a careful way so that alpha is always a positive number. But before we define alpha, let's clean up this notation a little bit. Remember when we talked about perceptron and all that, how do we define an error? When y and h have opposite signs, I can just say that yi times h of x is less than 0, right? In fact, in this case, y and h are exactly minus 1 or 1. So it's not just less than 0, it's equal to minus 1. And for here, yi ht of xi equals plus 1. So what we have here is when this quantity is plus 1, we need to multiply with a minus here. When this quantity is a minus 1, we need to multiply with a plus there. E power minus or e power plus. So I can combine everything and say e power y times this times alpha and minus of that. This is just a compact way of writing this. I've done nothing here other than just algebra. I have used up more space so that I can save some space in your code. But that's not done. So we have this. I defined dt plus 1 to be this quantity here. I've not told you what z is. I've not told you what alpha is. Z is nothing but a normalization constant. The goal of z is to make sure that all the d's add up to 1. If you have this numerator here, can someone tell me what z, how you would compute zt? I'll give you a simpler example. Let's say my dt plus, or let's not use d. Let's say I have some list A is the set I need to normalize this. These are all positive numbers. I need to normalize this so that every element becomes a number between 0 and 1. And the way I'm going to do that is I'm going to define a normalized is a divided by some z. What would that z be? 10. Why? I just add up these numbers 1, 2, 3, 4. Yes.
It should be the maximum amount.
It
It should be 4.
It could be 4, but then can it be 4? I want A normalized to add up to 1. If I divide by the maximum amount, let's try this out. In fact, oh no. If I divide, if Z equals 4, then A norm becomes 1/4, 2/4, 3/4, and 1.
So it should be summation of all.
It should be the summation. I add up by, I divide by the sum of all those things. Because everything there is positive, literally adding up these normalized things will take you to 1. So given that, what can ZT be?
Sum of DTI.
Is it sum of DTI or is it sum of DTI times this one? It's simply the sum of that strangely shaped thing that I'm circling now. Z is nothing but the sum of the numerators. It's like a simplest way of normalizing to add up to 1 that you can think of. That's what it is. There's nothing fancy about Z. Okay? And of course, for this to work, the numerator has to be more than 1, more than 0. But we started off with D was 1 over M, and we are multiplying by e power something, which is also a positive number. So we'll never get negative things. So this works out. But that part is easy. The part that's not so easy, so I'll just tell you the answer, is what is alpha? AdaBoost defines alpha to be this quantity here. It is half log 1 minus epsilon divided by epsilon. Epsilon is simply the error of the current weak classifier. What we want is alpha to be a positive number, because if alpha is a positive number, e power alpha is greater than 1, e power minus alpha is less than 1. We want alpha to be a positive number. Let's work it out. Epsilon t is less than half. Why is that? That's where we started the lecture today. We have a weak learner. The error of the weak learner is going to be less than half. It's definitely better than chance. It's the way, right? It's going to do at least better than chance. So it's going to be less than half. If epsilon is less than half, 1 minus epsilon is greater than half. That means 1 minus epsilon is greater than epsilon, because they are on different sides of half. That means 1 minus epsilon divided by epsilon is greater than 1. That means log of that quantity is greater than 0. And I say log, I mean natural log. So because we started off with the assumption that we have a weak learner whose error is less than half, this alpha is guaranteed to be positive. Because alpha is guaranteed to be positive, this whole thing ends up doing that promotion and demotion as we had hoped. Eventually, by the way, this alpha also becomes the weight assigned to this particular hypothesis. If your classifier, if your hypothesis epsilon had a very high error, that means, let's say epsilon is almost half, maybe just slightly less than half. That means 1 minus epsilon t is also almost half, just slightly more than half. The ratio of those two things is going to be nearly 1. It's going to be very close to 1. Log of that is nearly 0. So that particular classifier is going to get an alpha that's equal to 0. If you have a hypothesis that is really, really bad, according to epsilon t, then that hypothesis will get a very low weight at the very end. If your epsilon is nearly 0, then 1 minus epsilon is nearly 1. That means 1 minus epsilon divided by epsilon is infinite. Log of infinite is still infinite. That means if you have a weak learner that is perfect, it's not really a weak learner, then what AdaBoost says is assign infinite weight to that particular predictor because it's perfect. So a weak learner that's more accurate gets a higher alpha. A weak learner that's less accurate gets a lower alpha by construction. And that's the answer to the earlier question on how do we get these alphas. So we've answered this question of how do you construct this distribution dt? And along the way, we've also talked about how to measure these, how to compute these alphas. So let's wrap it up with a discussion on how do we actually construct the final output. After t rounds, we have t weak classifiers h1 to ht, and we have computed t values of alpha. Each weak classifier is a classifier. That means it produces a label that's either a -1 or a +1. The final hypothesis is simply the sign of the sum of alpha t times ht. For a new example, when it comes in, we give it to all these weak classifiers, h1, h2 till h capital T, ask them for their labels. So we have a collection of -1s and 1s. Weight each one with its corresponding alpha, add it up, check if it's positive or negative. If it's positive, we say that the consensus label is plus. Otherwise, we say the consensus label is minus. In the 2 minutes that are left, I'm going to just quickly put together everything we've seen into a single algorithm. We have a training set, x1 till xm. We have these where every label, every example is associated with the label yi, which can be -1 or 1. You initialize the weights to be all 1 over m. Every example is equally important. And learning proceeds in these rounds. In each round, you find a hypothesis whose classification error, weighted classification error, is better than chance. It's extremely important that the weighted classification error is better than chance, because otherwise, we don't get the property that alphas are positive. Then you compute its vote, the alpha. You compute the error along the way, and you compute the vote. And then you reweight all the examples. You update the weights. dt plus 1 is simply dt times e power minus y alpha y h of x for each example. And then you normalize so that you get back these numbers between 0 and 1. And you're done with this round. Then you keep iterating through these 3 steps for t iterations. And the final hypothesis is a function that takes the consensus as we described before. You can think of this picture here, that's useful. We have these 3 weighted, weak classifiers. And here's something that's not obvious until you think about it. It turns out that when you do this, your final hypothesis, which is also some sort of a separator, right, in the space. It's separating the plus, it's some shape that goes through the space. It might look something more complicated than any of the weak classifiers. It turns out what AdaBoost is actually doing is it's growing the hypothesis space to be the combination of your weak classifiers. It's really a combination of these 3 things, because this bit comes from here, this bit goes here, and this bit goes here. So your final separator looks more complicated than the any of the ones that you came up with. I'll stop here because the next thing that I want to talk about is actually the theorem that talks about the training error of this process. And then I'll talk about other complicated ensembles, and we'll do that on Thursday. All right, I'll see you Thursday. Don't forget your project thing. In the easy case, it just involves rerunning your homework code. In the slightly more difficult case, it involves fixing your homework code and rerunning it. Either way, get it done. And you always have the option of saying that what I uploaded does not count later on. So I want you to make some progress on the project. All right, I'll see you Thursday.